You know, Earth's climate has always been a story of change, right? It's been pushed and pulled by these massive natural forces for billions of years. But the big question today is, how did those ancient heavyweights, the slow wobble of the planet, a massive volcanic eruption, even the sun itself, how do they stack up against us? Well, today, we're putting them head to head. This is the tale of the tape.
So, who really is in the driver's seat of our climate right now? To figure that out, you can't just guess. You've got to measure the raw power of every single potential driver and put them side by side. So let's do that. Let's look at the actual numbers. And boom, right off the bat, this chart tells a huge piece of the story. I mean, this is the fundamental matchup. That big bar on the left, that's the warming influence from all human activities since we started burning fossil fuels. And that tiny little bar on the right, that's the entire energy swing from the sun's main 11-year cycle. The difference in scale is, well, you can see it for yourself. It's pretty stark.
Okay, let's put a hard number on it. Human activity is adding, on average, about 3 extra watts of energy to every single square meter of the Earth. I want you to burn this number into your brain for the next few minutes because every other natural force we're about to look at is going to be measured against this one. It's our benchmark.
And that measurement, watts per square meter, has a technical name: effective radiative forcing. But don't let the jargon throw you. Just think of it like balancing Earth's energy budget. If you get a positive number, it means more energy is coming in than going out, and the planet warms up. Simple. A negative number means it's cooling down. It's really the only way we can get an apples-to-apples comparison of all these different forces.
All right, first up in the ring, our contender from deep time, the slow, rhythmic changes in the way our planet orbits the sun.
These are the famous Milankovitch cycles, and they operate on timescales that are just mind-boggling. The shape of our orbit goes from circle to oval and back over 100,000 years. The tilt of our axis, that shifts over a 41,000-year cycle. These things act like a giant planetary metronome, basically setting the pace for the start and end of ice ages. They're incredibly powerful.
So here's the verdict on this one. Yes, these cycles are absolute titans of climate change, powerful enough to cover continents in ice, but they do their work over tens of thousands of years. The warming we've actually seen has happened since the 1850s, which is just a blink of an eye in geologic time. The timing just doesn't match up. Not even close.
Okay, next up are the contenders known for their quick jabs and sharp shocks, the sun and volcanoes. Now, what's interesting is that these two forces kind of work in opposite directions. The sun has its regular 11-year cycle where its energy output goes up and down just a little bit. On the other hand, a huge volcanic eruption acts like a giant sunshade, blasting particles into the stratosphere that reflect sunlight and cause a very sharp but very temporary cool down. Let's put a number on that solar cycle. From its weakest to its strongest point, the sun's energy changes the Earth's energy budget by about 0.24 watts per square meter. Now, remember that benchmark number, the human-caused one? It was positive 3.0. So the sun's entire up and down swing is more than 10 times smaller than the constant warming pressure from us. It's just not in the same weight class.
You know, you sometimes hear people say, what if the sun gets really quiet? Could we have a mini ice age? Well, NASA has looked at this very closely, and their analysis is clear. Even if we had a massive, prolonged solar downturn, like a really big one, it wouldn't be nearly enough to cancel out the warming from greenhouse gases. That mini ice age, it's not coming. Now let's talk volcanoes. They do emit CO2, for sure. But just look at the scale here. All the volcanoes on Earth, combined, spit out around 0.3 gigatons of CO2 a year. Humanity? We're putting out over 35 gigatons. We are out-emitting every volcano on the planet by a factor of about 100 every single year.
And that brings us to our final contender, the ultimate wild card, the low probability but civilization-endingly high-impact threat of an asteroid.
The classic example here is, of course, the asteroid that took out the dinosaurs 66 million years ago. A massive impact throws so much dust and soot into the air that it literally blocks the sun. You get years of darkness and cold, the plants die, the food web collapses. It's a true climate catastrophe. So this was a real existential threat in Earth's past, but here's the massive difference between then and now. Unlike the dinosaurs, we are actually looking up. We have developed something called planetary defense.
And this isn't science fiction anymore.
Back in 2022, NASA's DART mission intentionally smashed a spacecraft into an asteroid millions of miles away. And guess what? It worked. It changed the asteroid's orbit by a full 33 minutes. It was a proof of concept showing that if we have enough warning, we actually have the technology to nudge a threat out of the way. It's a risk we can now manage.
So, let's bring it all together. It's time for the final scorecard, the official tale of the tape.
And here it is, all laid out. Human activity is at the top, with a steady plus 3.0 watts per square meter, acting over decades and centuries. Then you've got the solar cycle, a tiny fraction of that, just wiggling up and down every 11 years. A big volcano gives you a temporary half-degree drop for a year or two. And the orbital cycles, well, they're playing a completely different game on a timescale of tens of thousands of years. The numbers really do speak for themselves.
So does this mean natural drivers don't matter? No, not at all. They absolutely play a role. The solar cycle creates a bit of noise around the long-term trend. Volcanoes give us these short, sharp cooling events. The orbital shifts are like the deep baseline of our climate, setting the stage over millennia. And asteroids, well, they're that tiny risk with huge consequences that we have to keep an eye on. But what these natural drivers don't do is explain the rapid, sustained warming we've seen since the Industrial Revolution. At the end of the day, it's like this. The slow, deep time drivers built the stage over millions of years. But the play that's happening on that stage right now, this incredibly fast warming act, is being directed by us.
And that really leaves us with a final, massive question. Now that we know the scale of each of these drivers, how should we balance our time, our money, and our focus? How much should we put into preparing for the short-term shocks, like a volcano, versus tackling the much larger long-term trend that is fundamentally reshaping our world?